Welcome to this lecture series in real analysis. In this lecture, we'll look at the notion of closed sets and let us recall what we need. So, we will need the notion of open sets. Recall that a subset U of R is said to be open if for each point x in U, there is some room around the point x, which means an open interval around the point x, which is contained in U. And we saw several examples of it, etc. We will need the notion of dense sets. So recall that a subset A of R is dense if for each point x in R, if you make an open interval around x, this open interval will intersect A non-trivially. And an example of dense sets was the set of rational numbers. Okay, and we will need the notion of subsequential limits. So if we have a sequence of real numbers, then a subsequential limit of this sequence is just any real number which can be obtained as the limit of some subsequence of this sequence. So those are subsequential limits. Now it's up to you if you want to include these things in subsequential limits. Depending on if you do, you will have to modify the corresponding statements that you make about this notion. I have not included infinity and minus infinity as subsequential limits. Okay, so let's proceed. Here are some problems for practice, and now let us get started. So what is a closed set? A subset F, I'm calling it F. I don't know if that is the best symbol. Let's say A subset A of R is said to be closed if its complement is open, and complement is this set. So the definition of a closed set is via an open set. If you take all the points that are not in the set, meaning if you take the complement of the set, you should get an open set. Okay, so the definition is very, very simple. Let's see some examples. So, examples of closed sets include, of course, the set of all real numbers, because what is the complement of all the reals? It is the empty set, and the empty set is open by convention. And by the same token, the empty set is also closed because the complement of the empty set is the set of all the real numbers, and the set of all the real numbers is open. Okay, so the real numbers and the empty set are closed sets. In fact, they are also open sets. So a set can be both open and closed. That's okay. Okay? Every singleton is a closed set. You pick any real number A, make this singleton. This is a closed subset of the set of reals. Because what is its complement? Its complement is this union that. This is an open set, that is an open set, hence the union of the two is open, because the union of any finite collection, or in fact any arbitrary collection of open sets, is open. So the complement of this guy is open, and hence this is a closed set. A similar reasoning will show you that any finite subset of reals is also a closed set. So try to prove this formally, but of course start with, let's say, the size of f being 1, which is the previous example. If you have the size of f is 2, you can again work it out, and from there you can build a general proof. This is a nice fact that every finite subset of the reals is a closed set. And closed intervals are closed. So such a thing is a closed interval where A is less than or equal to B. So these things are closed because, again, if you take the complement, you get this set. And this is an open set, that is an open set. The union is therefore open, and hence the complement of this guy is an open set. Therefore, this is a closed set. So these are some examples of closed sets. Okay. And again, just like we had properties of open sets, we will have properties of closed sets. So, yeah. So, first is that the union of any two closed sets is also a closed set. The proof is an exercise in set theory. So, let maybe A and B be closed sets. We want to show their union is a closed set. So, we will take the complement of the union and want to show that it is open. But what is the complement of the union? It is the intersection of the complements. So this is an exercise in set theory. If something is here, that means it is real and not here, which means it is real and not here and not here. And therefore it is in the intersection. Anyway, justify it. So the complement of A union B is the intersection of these two open sets. Why are these two open? Because A and B are closed. So by definition of closedness, these are open sets, and the intersection of any two open sets is open. Therefore, this is open, and that's it. That finishes the proof. And similarly, we have, this is just an extension of the previous one. The union of finitely many closed sets is closed. You just apply the previous one repeatedly. Formally, you can prove it using mathematical induction or the well-ordering principle. Okay. This is slightly more interesting, but also an exercise in just set theory. So the intersection of any collection of closed sets is closed. Just like we had the union of any collection of open sets is open, and it will follow from that. So suppose we have a collection of closed sets. And let A be the union of all of them. And we want to show that A is closed. Sorry, what have I written? Take the intersection of all of them. We want to show that A is closed. So to show that A is closed, we will take the complement. But the complement of the intersection is union of complements. Right? So this is also just a set theoretic thing. You have a real number which is not in the intersection of the A alphas. Right? So it is not in each A alpha. It could lie in some of the A alphas, but not in all of them. So it has to avoid some A alpha. So there is some alpha for which that point that we chose is not in A alpha, and hence it's here somewhere. So this containment is justified. Similarly, you can justify the reverse containment. Anyway, so this is true, and therefore R minus A, or the complement of A, is the union of a bunch of open sets, because each A alpha is closed. So this is open, and hence this is open, because the union of any arbitrary collection of open sets is open. So this is open, and hence A is closed. So that's the proof of this guy. And these properties will be very useful. Okay. Now, for convergence, this is kind of the first somewhat non-trivial fact that we are going to prove. So there is a connection of closedness with limits of convergent sequences. So what is it? You pick any non-empty subset of the reals, then these two statements are equivalent. The first is that A is a closed set. The second is that whenever we pick a sequence of real numbers such that each element of the sequence is in A, in other words, we are picking a sequence in A which is convergent, then the limit of the sequence will remain in A. It cannot go outside A. So a set with this property is exactly the same as a closed set. Okay, so let's try to prove this. So first, we will prove this direction. So assume A is closed, and let Xn be a sequence in A such that Xn is convergent. So let Xn be a convergent sequence in A is what I should write. right? So we have a convergent sequence in A, and we want to show that the limit of this sequence is in A. All right, so let's say X is the limit of the sequence, just a notation, and we want to show that X is in A. All right, so if X is not in A, so assume on the contrary that X is not in A, that is the same as saying X is in A complement. Okay, X is in A complement. And now let me try to explain the remaining proof via picture or via some graphics, and then we will write it down. So somewhere we have a set A, which we have assumed is closed, and we have chosen a sequence of points in A and assumed that the limit of the sequence is outside the set A, and we want to arrive at a contradiction. So this is the limit of the sequence. And now, since the complement of A is an open set, right, the complement of A is an open set, so X is in the complement of A, and therefore there is some room around X which is contained in the complement of A. Right, the complement of A is open. We have chosen X in the complement of A, so there is some room around the point X which stays away from A, and therefore no points in the sequence that we had started with can lie in this region. But at the same time, by the fact that this sequence was converging to the point X, ultimately they must lie in this region, because this is just some open interval around X, and that is a contradiction. So that's the scheme of the proof, and that's exactly the proof. So let's just write it down. So since X is not in our A complement, and since A complement is open, we can find epsilon greater than 0 such that this is contained in the complement of A, which is to say that this interval does not intersect A or intersects A in the empty set, which implies that Xn does not belong to this interval for any n. I mean, so this not belongingness is true for all n. So this is for all n. Why is this? Because this interval does not intersect A, so it does not contain any point of A, and all the points of the sequence are points of A because the sequence is contained in A. So in particular, this will not contain any point of the sequence, but this contradicts the fact that but we already knew that Xn is here ultimately, because X was the limit of Xn, and that is a contradiction. So that proves 2. So this is a contradiction proving 2. And now we want to do the other direction. So now assume 2 and we will be proving 1. So let A be some subset such that A satisfies 2. We want to show that A is closed, which is to show that the complement of A is open. All right. So fix some point in the complement of A. Fix some point in the complement of A, and we want to show that there is some room around the point X such that this room is entirely contained in the complement. So the reduced goal is to show that we want to show that there exists epsilon greater than 0 such that this open interval around X is contained in this, which is to say that this open interval does not intersect A. Okay. And now, yeah, what is the easiest way to? I don't want to go via contradiction, but perhaps I will have to. Okay, so let's go via contradiction. That's what immediately comes to mind. So assume on the contrary to this last statement. So if there is no such epsilon, then for all natural numbers n, there is a point in A which also lies in this open interval. Now this has to be understood. So we are assuming on the contrary to this. This is what we want to prove. Once we prove this, we will have proven that. So this is our goal. And if we assume on the contrary to this, then in particular, for each n, you will have that this interval around x has to contain some point of A. Because if it doesn't, we will have found an epsilon, which fills the bill. So for each n, there will be some open interval around x, which contains a point of A, and let's say xn is one such point. So we have chosen a point xn in this intersection. And now just note that. So, but then xn converges to x, basically. Why is that? One can justify it by writing a few lines, but here is the thing. Xn is not too much away from x. It is at most 1 by n distance from x. And as n increases, this distance decreases. So xn will converge to x. You can justify it if you like. I mean, this is a good enough justification, but you can be even more formal. You can say that, well, pick an epsilon greater than 0, and then you can show that x minus epsilon comma x plus epsilon, this interval ultimately contains xn. Anyway, so this is true. But now what happens? Each xn was a point in A, and it is a convergent sequence as we showed. So the limit of the sequence, by the fact that A satisfies property 2, the limit of the sequence should be in A. By the nature of A, therefore, x is in A, and that's a contradiction to the choice of x, because x was chosen in A complement. So this is a contradiction, and this finishes the proof of 1. Right, so we have a nice criterion to decide if a subset of the reals is closed. This criterion is in terms of convergence. Okay. So here is a nice example of closed sets. You pick any sequence in R, meaning a sequence of real numbers, and S be all the subsequential limits. So just the set of all the real numbers that can be obtained as the limits of some subsequence of this guy, then that set is a closed set. So this is one way to build closed sets. So the set of all the subsequential limits is a closed set. Okay, why is this? Again, you should take this as an exercise before looking at the proof, because this is very instructive. So we will use the previous proposition to establish this. I'm sure there are other ways, but let's use the previous proposition to establish this. And what we want to do is, so let S1, or rather let Sn be a sequence, be a convergent sequence in S, and say S is its limit. And we want to show that S is in capital S. So suffices to show, or want to show, whichever you like. Want to show that S is in capital S. And once we do this, we will have established that S is closed because of the previous proposition. Okay, so this is our goal. So we want to show that this guy is also a subsequential limit. Little s is also a subsequential limit is what we want to do. So we will build a subsequence which converges to it. Right. So for each n, so each Sn is a subsequential limit. So for each n, and here is the statement that one has to be very clear about. Let me write the full statement. Since each Sn is in S, so the way to write it is since Sn in S for each n, which is to say that each Sn is a subsequential limit, we can find x1, x2, I shouldn't say x1, x2, x3. We can find indices k1, k2, k3 such that xk, xkm and sm are not very far away. All right. So yeah, so this has to be understood well. Basically, since, or rather first you fix some m, or let's start with S1. So S1 is a subsequential limit. So there is some xk1 which satisfies this inequality, because if there is no index k1 for which this happens, then all the points of the sequences are away from S1, a lot away from S1, if this were contradicted for any index. So there is some k1 which satisfies this. In fact, there are infinitely many such k1s, because there is a whole subsequence of the original sequence which converges to S1. So there are infinitely many k1s. Similarly, there are infinitely many k2s such that this happens by the same reasoning. This time we have written a half. And there are infinitely many k3s for which this happens, right? So once you pick a k1, there are infinitely many k2s which satisfy the second inequality. So you just pick a k2 which is bigger than k1. Now you have k1 and k2, so now you pick a k3 which is bigger than k1 and k2, because there were infinitely many k3s which were available to us. So we can pick one which is bigger than k2, and we can build a subsequence of xn with this property. So this is true for all m. So I hope that reasoning was clear, because that is crucial to this proof for all m. Okay, and now note that therefore xkm is convergent, and in fact its limit has to be same as the limit of Sm, which is S. So again, this also has to be justified. The point is, Sm comes closer and closer to S, right? As m increases, Sm comes closer and closer to S, and xkm comes closer and closer to Sm. Xkm and Sm has very, very small distance, and as m increases, the distance becomes smaller and smaller. So the distance between S and xkm has to be also smaller and smaller. So this is just a triangle inequality argument, but the colloquial way of saying it is just this. Sm is coming closer and closer to S, and this is coming closer and closer to Sm. So these two are also coming closer and closer, and therefore this one converges to S. But again, write down a formal proof if you're just a beginner with these arguments. So we have constructed a convergent subsequence of the original sequence which converges to the point S, and this is what we wanted to do. This shows that little s is a subsequential limit and hence an element of capital S, and this is what we wanted to do. So we have proven this lemma. Okay. Now finally, we will discuss what is meant by the closure of a set. Just like we had the notion of the interior of a set, we also have the notion of the closure of a set. So the idea, just like the interior captured the largest open set contained in the given set, the closure of a set measures how closed is a set. So let's define it. To fix a non-empty subset of reals, the closure of A is defined as the intersection of all the closed sets that contain A. Right? So, first of all, for this intersection to mean something, or for this intersection to even be defined, the set of all the closed sets which contain A should be a non-empty set. Meaning there should be at least one closed set that contains A, and there is the set of all the real numbers. This is a closed set which contains A. At the same time, every closed set that contains A, and hence this intersection contains A. Alright, so I'm saying some tautological things. So the closure of A is written as this symbol. We put a bar on top of A. That is the closure of A by notation. And it is by definition the intersection of all the closed sets that contain A. This collection of closed sets which contain A is a non-empty collection, and each element of this collection contains A. So this intersection is well defined, and this is the case because each element of this collection of closed sets which contain A contains A. So the intersection also contains A. This is that intersection, and therefore it contains A. So A closure is a closed set which contains A. Why is it a closed set? Because it is the intersection of a bunch of closed sets. The intersection of a bunch of closed sets, no matter how big that collection might be, is always closed. This is what we proved. So the closure of A is a closed set. Please note this. All right. And this immediately captures the notion that the closure of a set is the smallest closed set that contains A. Any closed set that contains A will be containing the closure because we are intersecting all the closed sets that contain A to obtain the closure. So we have that with us. And now let's just prove one lemma and be done with this. Maybe then we will see some examples and then we will be done with this. So what is the lemma? The lemma is let A be a subset of R. Then X is an A closure if and only if for all epsilon greater than 0 this intersects A non-trivially. Okay, so this is the last proposition of this lecture. So all we are saying is that X is an A closure if and only if every room around X intersects A non-trivially. This statement is very, very simple. The proof is also just a follow your nose argument. So let X in A closure be arbitrary. And we want to show this thing. We want to show that for all epsilon greater than 0, this room around X intersects A non-trivially. So if we assume on the contrary, that there is epsilon greater than 0 such that the corresponding room around X intersects A trivially. Alright, call this thing U. This is in particular an open set. So the above statement is just the same as saying A is contained in R minus U. This intersection being trivial, meaning empty set, It's same as saying that A is contained in the complement of this guy. But this is a closed set. U is an open set, therefore this is a closed set. So this implies that the closure of A is also contained here. The closure of A is the intersection of all the closed sets which contain A. And this is one closed set that contains A. So closure will be contained here. Fine. But this implies X is not in A closure. Why? Because X is here, and this shows that A closure is completely away from U and hence from X. X cannot be therefore in A closure, and that's what we have here, but that contradicts the choice of X. I have to say not. Yeah, so this shows that X is not in A closure, but we started with the assumption that X is in A closure, and that's a contradiction. So this direction is fine. So we started with this and proved that, and now we want to prove the reverse direction. So now for the reverse direction, let X be such that X be a real number such that for all epsilon greater than 0, this room around X intersects A non-trivially. We want to show that X is in A closure. But if X, wanting to show that X is in A closure is same as asking that X is in every closed set that contains A. So suppose not, again going by contradiction, suppose not, then there is a closed set. There is a closed set F of R, of course, such that X is not in F. Right? Because if X is not in A closure, there must be some closed set which contains A in which X does not lie. So there is some closed set F such that X is not in F and F contains A. That is the contrary to the statement that X is in A closure. Fine. So we have that. Therefore, X is in this thing, the complement of F. But since F is closed, the complement of F is open, which implies there exists epsilon greater than 0 such that the corresponding open interval around X is contained in this thing. Right? Since this is an open set, because F is a closed set, you can find a room around X which satisfies this property. But if this is the case, then in particular, not in particular, this is true. This is exactly the previous statement. This is contained there is same as saying this intersects F in the empty set, but F contains A. F is a closed set containing A. So instead of F, we can write A. And that is something in particular true. Okay, so this intersection is empty, and that is a contradiction because X was a point such that whenever you choose epsilon greater than 0, you have a non-trivial intersection with the room around X and A. And here we are contradicting that. So at any rate, you get a contradiction, and therefore this equivalence is true. So that's a very nice characterization of closure of a set. And before we proceed, let me note here that a set is closed if and only if, maybe I'll note it here, A is closed if and only if it's its own closure. And take this as an exercise. All right. Here are some examples. Take any open interval, then the closure of this guy is this. And use the previous proposition to establish this. Take this as an exercise. As we already noted, this is contained in A closure. A is contained in A closure, so a lot of points have already been accounted for. You just have to argue that little a and little b are also in A closure. That is very simple, because if you make a room around the point A, it has to intersect this. So therefore little a is here, and similarly little b is here, and no other point is in the A closure, and that is also very easy. Fine. If A is the set of all the rationals, then the closure of A is everything. Is the entire set of real numbers, because the key property here is the denseness of Q. So more generally, A bar is R if and only if A is dense. So this is a full characterization of dense sets. You are given a set, you want to know whether or not it is dense, you take the closure. If it is the entire set of real numbers, it is a dense set. Otherwise, it is not. And again, just use the previous proposition. Suppose we have a dense set. Then we want to show A closure is equal to the entire set of real numbers, which is to say that every open interval intersects the set A. That's exactly what it means. Saying A closure is equal to R is exactly the same as saying every open interval intersects A. But every open interval intersecting A is also the same statement as A being dense. So therefore, this is an if and only if criterion, and in particular, the closure of the rationals is the reals. What about this guy? Well, here A closure is this set. So, if you take, since these points converge to the point 0, if you make a room around 0, it will always intersect this set. So 0 has to be in the closure of A, and no other point is in the closure. That I leave as an exercise. More generally, if we have a sequence of reals, and A is the set of all the points in the sequence, then the closure of A is A union all subsequential limits. Okay, I hope I'm not making a mistake. I'm pretty sure this is true. Let me just think for a moment. Yeah, so it is clear that this and that are both contained in A, because A closure is a closed set, and if you have a convergent subsequence in A, it is also a convergent subsequence in A closure, and hence its limit must lie in A closure because A closure is closed. So this much is definitely contained in A closure. And why is this all of A closure? Well, if we pick something which is away from here, which is not a subsequential limit and is not an element of A, then we want to show it cannot be in A closure. But if it is in A closure, then every open interval around it will intersect A, and then you will be able to find a sequence of points in A which converges to that, and hence it will become a subsequential limit. Yeah. So yeah, that is fine. So we have this. You can write down a formal proof. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.